to me, just adding them up. Because then I'll keep all my accelerations on one side and the FTs will just go away. Because I have a positive FT and a negative FT, when I add them,
Yeah.
they annihilate in the burst of light. So I'm left with mu k m3g cosine theta plus m3g sine theta plus m2g equals m3a plus m2a. We factor a out, so I get m3 plus m2 times a, and then do a little division to solve for a. So a equals this grand formula, u sub k, m3g cosine theta plus m3g sine theta plus m2g divided by m2 plus m3.
Can we take out the m's?
Yeah.
Wait, no, we cannot because there's two different masses. We cannot take out the m variables because there's two different masses, right?
Correct.
So,
Or to put it in a position where we can, it's easier just to plug the numbers in. Now notice I've got force divided by mass. This is the total force that's trying to slow that thing down. So if I think about this as one object, I've got that weight, I got part of that weight, and I have friction all trying to slow it down. That's what I have on top. Denominator, I got two masses, it's the total mass on the bottom. If you see that initially, that is a shortcut for this problem. Trouble is, some people try to take that shortcut for every problem, and it doesn't always work. Like on the last problem on the chapters 4 or 5 application, master set. Plugging chunk. So that is equal to 0.3 times 3 times 10, because Earth 2, times the cosine of 40 degrees plus 3.
Wait, can you like say what these numbers are? Well, I get the 0.3 and then 3 is the mass.
Yep.
Right, okay,
Earth 2, g is 10 meters per second squared.
okay,
And then the 40 degrees comes from the 130 minus 90.
right, okay, I'm with you.
Okay. That's not right on the bottom.
It's supposed to be 5, right?
Just 2 plus 3. Get the acceleration of 10.3,
I got 9.09.
9.09 for A.
9.236.
I got 9.236.
If this were the answer, what would it be?
Meters per second.
Did you say the last bit? All right, we got a positive acceleration because we chose our coordinate system to be positive in the direction of acceleration. So we got a positive number, that's expected. If we'd chosen our coordinate system going the other way, we would expect acceleration to be negative. We'd have a negative value there.
So you got, okay.
All right, we seem to have a groundswell of 9.236. Now the second part of the problem is how far up the ramp does it go? This is a chapter 2 motion problem. I have displacement, which is what I'm trying to find. My initial velocity is,
10 meters per second.
No, that's the initial speed.
well, what is the acceleration?
9 point, oh, it's supposed to be negative 10 meters per second.
If we're gonna keep the same coordinate system so that that's positive, this is negative. Acceleration and velocity are in opposite directions.
So we can change the coordinate system?
If you want. Because basically, we've established the acceleration is down the ramp 9.236 meters per second squared.
Yeah, right.
So
So it would-
we've gotten everything we need from this.
So the initial will be a negative 10?
So we could switch the coordinate system if you wanted, because it's treating it like a brand new problem. Just remember to put the minus signs in the right place. If we keep this coordinate system, then this would be negative 10 meters per second. Acceleration 9.236 meters per second squared. All right, or you had a question?
That was my question. You said it, I was confused about, I thought you were saying we were gonna make the acceleration negative, and I didn't understand because I had an acceleration.
Yeah, keep it, but it was asked if we could change it. Yes, we could, just make sure that those signs would flip if you did. And, let's see, final velocity, we know, and time, we don't know. All right, final velocity? I know 3 things here. All I need to know, the question is for displacement, which one? Which equation? Acceleration will be constant as long as the forces are constant, so therefore, the forces are constant.
Velocity times time plus half the acceleration times time.
If you wanted to, you could solve for time first and then solve for
The
displacement.
VF squared equals VI squared plus 2A displacement.
So I have 0 squared is equal to negative 10 squared plus 2, that's 9.236 times delta S. I do expect delta S to be a negative number here, because we have down the ramp as positive and it's moving in the negative direction. So my displacement should be negative, which it will be. That's 100, so I have negative 100 divided by 2 times 9.236.
Wait, how's it negative 100?
Yeah, it should.
Because negative 10 squared is 100, and then if I bring it over to the other side, the negative appears.
Negative 81.
What is it?
Negative 81.528.
No.
Is that?
No, I can't.
Oh, wait, I added them.
Okay.
Negative 461.
Negative 5.414.
What did I do?
That makes more sense, because this is a little bit under 10. 2 times 10 is 20. 100 divided by 20 is 5, so it's gonna be the ballpark of 5.
It's fine.
Negative 5.
All right,
Classic.
So this is one-dimensional motion.
yes,
Why?
because the ramp is supposed to be straight. The ramp is straight, the mass is moving in one direction.
Right, but there's an angle though.
Yeah, but the mass itself,
Okay, so we're doing just that part.
well, the other part, the 2 kilogram mass, the one that's moving straight up, is also moving in one direction. The 2 kilogram mass has already been taken into account. The 2 kilogram mass affected that number right there. The acceleration was determined by both masses. So now we have that, we have to think about it. More importantly than just one-dimensional motion, it's constant acceleration. before there's, as it slides up, before it stops, there's nothing that would change here. Forces are constant.
Okay, so for the displacement, I just wanna make sure I understand this correctly. You're saying it's negative, but my brain wants it to be positive because it's going in the same direction as what we determined I have as positive, but is it because it's relation to starting point or origin? I can't remember.
Displacement is based upon starting point.
Okay.
Yeah, we did not establish it as an origin.
Right, there is no.
What is actually the final answer? It's displacement. So it's gonna go up the ramp 5.414 meters. The question is it gonna come back down?
You have to use static. You have to use a static friction then, right?
So now, all right, so we have to use static to see if we overcome that. And what's the other thing that's gonna change?
The speed? No.
Instead of 0.3, 0.4.
Okay, well, that's using the static. But there's another change, there's a change to the force diagram.
The direction.
Oh, that's all.
No, it's actually the same.
Right, I heard several things at once and understood none of it. Try again?
You're asking what's changing?
Yeah,
The direction of acceleration?
the acceleration would
Like
still
the
be down
box
the
is-
ramp if there is any.
Now the box is going the other way.
Well, we're trying to figure that out. But if it were frictionless, the box definitely would go the other way. Therefore,
Friction.
what changes is the friction now flips.
Okay.
So it gets up to a point of stopping, so friction's acting down the ramp, it stops, it magically flips this way.
That makes sense.
And so what would change is too far.
Everything. It's gonna be subtraction signs.
That becomes mu sub s, and that becomes negative.
And then see.
So mu sub s, negative. Negative there, mu sub s, negative 0.4. If we end up with a positive answer, then it will accelerate in the direction of positive acceleration, which is down the ramp. Negative acceleration means that it would have to accelerate up the ramp from a stopping point, and that is not physically possible without additional forces.
I'm just curious, but let's say I put the J hat 3 parallel to the weight, how would you decompose the normal force?
But if you J hat,
Parallel to the weight, to the gravitational force, so weight 3. How would you decompose normal force?
all right, these need to be perpendicular to each other.
Oh, okay.
So if you make that go down, then that is either gonna go left or right.
Okay,
And you've now quadrupled the amount of math you have to do.
alright.
I do go through there's a video where I go through a problem where I do the classic, just box on ramp, and I do the classic setting it up like this. And then I solve it again with like this for those who want to do it that way. And just, you end up with two components of acceleration. There'd be an AX, AY, or A1, A2, or A1 squared plus A2 squared equals A squared. And, yeah. And fun was had by all. More than Naomi?
So if we were to solve for static, it does give us a negative number, so that just means it doesn't slide back down? It
Correct.
uses a stopping point and just stays stopped?
Yep.
Okay.
Although, I'm surprised by that.
The -4 times 3 times 10 cosine 40 degrees
Yeah.
all ends up being a bigger number than the rest of it,
Because that's 20 right there, and that's,
not as big.
okay.
Could be right, somebody else check it.
So, you go. Yes. 0.7. 12 times 0.7, because that's 0.3.
That's
Point four.
0.4.
Negative 0.4, right?
Oh, that's what I did wrong.
That'd be like 4 times 3.
Never
so
mind,
it's
I
12.
forgot the decimal in the
Okay, yeah, that'll do it. And then if the question were, what's the acceleration down the ramp, then you'd have to plug use of K in, and the fun would just keep
So
going.
it will be like that.
So, it's,
So my question was, so the negative 0.5 for 14 meters is how far it will go up the ramp, right? And it's negative because we said the acceleration was down.
And we said that that was the positive direction.
Okay.
So we're gonna get a positive answer for this, which means it's gonna slide back down.
Yes. The question officially that I asked in the beginning was, would it slide back down? So the answer is yes. If the question is, what's the acceleration? If it does slide back down, what's the acceleration?
So that's
Well,
literally that.
you plug the 0.3 back in there because it is sliding and solve.
So we use static friction because, why did we switch to static?
So while it was moving up the ramp, it was sliding. We use kinetic. Once it stops, if the velocity is 0 or speed is 0, then we have to see, is it going to overcome the static friction? So we have to plug in use of S to see if it overcomes it, which apparently it does unless you leave off the decimal point.
Can we go over one more time how you get the cosine and the sine? I don't understand. What does that have to do with the angle?
Alright,
So how does that?
breaking weight up, whatever I'm breaking up, whatever I'm decomposing is the hypotenuse of a triangle. So I have weight acting down. So if this is, say, 40 degrees, if that's a right angle, what is this angle right here?
The theta point. Theta point.
Or more specifically in this case, 50. All right,
Okay.
now if I break it up, I've got part going down the ramp and part going perpendicular, that's a right angle there. And so if that's 50 degrees there, what's that angle right there? Well, I got a right triangle, that's 50.
What?
If I gave you a right triangle like this, that's a right angle, and that's 50 degrees. What is this angle down here?
Why are we? Okay.
The reason why I get it in terms of 40, I could have done it with in
I
terms of 50.
understand how you get the points, I'm just, why are we making it a triangle?
Because we actually need to break up weight into its components.
Remember the crazy diagram that's not repeated, that has all the diagrams and they're talking about tip to tail and like the result?
Yeah.
Is that basically what this is?
Yeah, this is sort of the reverse way.
Did
Okay.
you start on
In that lab, you started with,
But
no, it is like this.
But like, what does that have to do with where we know where cosine and sine is on the box?
All
How
right.
does that relate?
The reason why I get this, I want to find the 40-degree angle is it's the same angle as this one down here.
Right.
All right, now look at this triangle right here, if I know this is 40 degrees, I know my, that's a W. My opposite side right here deals with sine.
Yeah, that's not sure
So
about
that's
my
the
mouth.
hypotenuse times the sine of the angle.
And then the other side would be cosine.
Yeah,
Like,
and so that's why sine was down the ramp, cosine was into the ramp.
oh, so okay. So that's like the ramp, we're looking,
This,
so we're looking at the opposite of, like, the reflection of what it would be on the
I
box.
said it would be.
Because your triangle is coming like from
So it
the
should
ramp.
return to the starting point.
Does that make sense? I think I know what you mean.
Oh,
I
it's
think
like
I
I'm
know
drawing
what
my
you mean.
angles in all sorts of directions.
So if we were just like looking at right on top of the ramp, we would
Yeah,
just
so,
would say that the top of it would be the sign. Okay, no, yeah, that makes sense, that makes sense. Yeah, okay, yeah.
you say your papers?
oh, dang it!
one?
What?
Oh, yeah, great.
It's a good thing they,
No, I wanna see those.
I wanna see mine.
that's just a
I'm kinda disappointed.